Welcome to today's deep dive. I am your host.
And I am your resident expert.
The other morning, I was actually walking down my driveway. It is just a gravel driveway, nothing fancy at all.
Right.
And I found myself just sort of kicking the stones. You know how you do that?
Oh, yeah.
You were waiting for a ride or maybe just checking the mail, and you were just kind of nudging these gray, dusty little rocks around with your toe.
That's idling.
Exactly. And I had this thought, which I think is a pretty universal one. To the average person, a rock is just, well, it's just a rock.
It's hard. It's heavy.
Right. It just sits there.
It's aggressively opaque.
Aggressively opaque. I like that.
You cannot see inside it. It is essentially a closed book.
And that is the standard human experience with geology, really. For most of human history, a rock has been a tool or a weapon or just an obstacle.
Something in the way.
Right. It is something you build a wall with or something you trip over in the dark. It is effectively dead matter.
But then I started digging into the stack of research we have for today.
And it is a massive stack. It really is. We have everything ranging from a heavy-hitter technical manual on microscopy by Wraith, Race, and Reinhardt.
Which is brilliant, by the way.
And we have a university-level overview from LibreTexts on optical mineralogy.
Plus some really practical field guides on acid testing from Script.
Which sounds both dangerous and fun. Oh, and an informal video tutorial transcript from GeoGirl.
That one really breaks down the visuals nice.
It does. And we are even rounding it out with U.S. Department of the Interior museum directives on how to handle all these things.
Very eclectic mix.
Yeah. But going through all of this, I realized I have been completely wrong about rocks my entire life.
How so?
Well, I have been looking at rocks, but I haven't been looking through them.
Ah, yes. And that preposition, looking through that, is the critical distinction here.
It changes everything.
It changes geology from a study of shapes and dust to a study of light.
Because if you slice that dull gray rock thin enough...
And we are talking very thin.
Right, paper thin. Actually thinner than paper, thinner than a human hair. And you put it under the right kind of microscope, it doesn't look like a rock anymore. It looks like a psychedelic light show.
It is stunning.
It is all neon blues, hot pinks, these shifting rainbows. It is basically a stained glass window made by nature, but on a microscopic scale.
And it is a transformation that never really gets old, no matter how many years you spend in the lab.
I can imagine.
You take something that seems dark and inert, and suddenly, using the physics of light, you reveal that it is actually a frozen history of the Earth.
A frozen history?
Yes. You can actually see the magma cooling. You can see the stress of continents colliding.
Just in the colors.
All locked in that little slice.
So that is our mission for this deep dive. We are going to take you, the listener, on a journey from that dusty gravel path right down into the molecular lattice of a crystal.
We are going to turn that gray stone into a kaleidoscope.
Exactly.
And to do that, we have to talk about scale.
Right.
We are going to start with the tools that let us see the invisible. Specifically, the Petrographic microscope, which is a total beast of a machine.
A beast of a machine.
Then we will dive into the physics of light itself, how we twist it, how we manipulate it to essentially interrogate these minerals.
I love that concept.
And finally, we are going to zoom back out to the administrative side of things, how we organize and preserve all these physical samples so that the knowledge doesn't get lost.
Because if you lose the rock, you lose the history.
Precisely.
So let's start with the hook here. You've described optical mineralogy to me before as detective work.
It absolutely is detective work. Think about it. When you pick up a rock in the field, you are mostly guessing.
Right. You say, oh, that looks like granite because it's speckled.
But you don't actually know.
Right.
To know, you have to interrogate the crystals. And you cannot just ask them.
Obviously.
So you have to use light as your interrogator. You force light to travel through the crystal, and you watch how the crystal fights back.
How the crystal fights back. That is such a great phrasing.
But it's literal. You ask, does the crystal slow the light down?
Does it split it?
Exactly. Does it split the light into two separate rays? Does it absorb certain colors and let others pass?
So it leaves a fingerprint.
Every single mineral has a unique fingerprint of how it messes with the light passing through it. Our job is just to read that fingerprint.
Okay, so before we can see the fight, we need the arena.
The arena being the microscope.
Right, the petrographic microscope. Now, most of us remember microscopes from high school biology class.
The classic classroom scopes.
Yeah, you look at an onion skin, or maybe you look at a bug leg. You turn the knob, the bug leg gets big. Is this the same thing?
Well, physically, if you walked into a geology lab, they would look similar.
They have a tube.
A tube, a stage, some lenses. But the petrographic microscope has some superpowers that your biology scope definitely didn't have.
Okay.
However, before we get to the superpowers, we have to respect the basic engineering,
The math.
the math. The Wraith text makes a very big deal about the math of the lens. And I think we should unpack it because it explains why we can see anything at all.
Let's do it.
Okay.
Because the sources get into the math, and I want to decode it. I rarely get to use algebra in real life.
It is a rare treat.
So we are talking about a compound microscope.
And compound just means we're using two lens systems to get the job done.
Not just a magnifying glass.
Right. You have the objective lens,
Hmm.
that is the one down near the rock, and then you have the ocular lens, or the eyepiece, up top,
And the formula they lay out, the lens formula, is 1 over A
plus 1 over b,
equals 1 over F.
a classic equation in optics.
Okay, lay it out for me. What are we actually measuring here?
It is a relationship between three specific things. First, F is the focal length of the lens.
And that's fixed, right?
Yes, that is a fixed property of the glass itself. The curve of the lens determines it. You cannot change F unless you physically unscrew the lens and put in a totally new one.
Okay, so F is a constant.
Right. Then you have A, that is the distance from the object, the rock, to the lens.
Okay.
And finally B, which is the distance from the lens to the image it creates inside the microscope tube.
So it is essentially a balancing act. The equation always has to equal out.
Precisely. And this is the part people don't realize they are doing when they focus a microscope.
When they're twisting the little knobs.
Right. You aren't just making the image sharper by some kind of magic. You are physically changing A.
The distance to the rock.
Yes. You are moving the stage up and down, changing that exact distance between the rock and the lens.
Because F is fixed.
And the tube length, B, is usually fixed. So there is only one specific distance, A, that satisfies the equation.
So when I'm looking through it and the image is blurry, it just means I have broken the math.
It means the equation is currently unbalanced. The image is forming somewhere, but just not where your eye can actually see it.
But then you move the stage.
You move the stage until the math works, and snap, the image appears perfectly crisp.
The text actually made a really interesting comparison to the human eye here. Because our eyes are lenses too.
They are. But they are organic, squishy lenses.
Squeezy lenses.
This is the grand difference between biology and engineering. When you look at your phone in your hand, and then you look up at a mountain way off in the distance, you don't physically move your eyeball forward and backward in your skull.
That would be horrifying.
It would be very unsettling to watch.
Very.
Instead, tiny muscles inside your eyes squeeze or stretch the lens itself.
So you were changing the curve.
You were actually changing the focal length in real time.
Yeah.
You have a variable shape lens.
Which is wild engineering by evolution when you think about it.
Truly incredible. But a microscope lens is made of glass and brass. It is rigid.
It definitely cannot squish.
No.
Yeah.
So instead of changing the lens shape, we have to change the distances. That is why the mechanical quality of the microscope matters so much.
If the gears slip.
If those gears slip even a tiny bit, the math breaks and you lose focus.
Okay. So we have lenses magnifying things. But there's a trap here, isn't there?
A very big trap.
Because I think a lot of people, myself included, assume that if you want to see something smaller, you just need more magnification.
Just crank it up.
Right, just make it bigger. If 100x is good, 1000x must be 10 times better.
Ah, yes. The bigger is better fallacy. This is probably the most common misconception in all of microscopy. We call it empty magnification.
Empty magnification. That sounds oddly judgmental.
Well, it is accurate. Think about it this way. Imagine you have a really blurry photograph on your phone.
Okay.
If you pinch the screen and zoom in on it, does it get clearer?
No, the pixels just turn into huge blocks.
Exactly. You have increased the size, but you haven't added any actual information. Magnification is just expanding the image size.
So making it bigger doesn't help if it's a bad image.
Right. What you actually need is resolution.
Resolution, meaning sharpness.
Technically speaking, it is the ability to distinguish two closely spaced points as separate entities.
Okay, give me a visual for that.
If your resolution is bad, two tiny bacteria sitting right next to each other just look like one big blob.
Just a single smudge.
Right. And no matter how much you magnify that blob, it is still just going to be a blob. You need to resolve the gap between them.
So what controls this resolution? Because the sources got really technical here about something called numerical aperture, or NA.
Numerical aperture. This is the single most important number stamped on the side of a microscope objective.
Really? More important than the magnification.
Absolutely. If you look at a professional lens, it will say something like 40x over 0.65.
Okay.
That 0.65 is the numerical aperture.
And what does that number actually represent in the physical world?
Think of the lens as a bucket catching rain. The rain is the light reflecting off the tiny details of your rock sample.
So light is bouncing off the rock and up into the lens.
Right, and to get a high-resolution image, you need to catch as much of that light as possible, specifically the light coming off at very wide angles.
So a wider bucket catches more information.
Correct. The NA is essentially a measure of how wide that light-catching cone is. The formula for it is NA equals N times the sine of alpha.
Okay, let's break that down for everyone. Alpha is the angle of the cone.
Right, and we want that to be big.
We want a wide bucket, but N is the tricky part here.
Very tricky.
Because N is the refractive index of the medium between the lens and the rock.
And this is where physics essentially punches us in the face.
How so?
Usually the stuff between the lens and the rock is just air.
Just the air in the room.
Right, and air has a refractive index of roughly 1.0. It is the baseline.
Okay.
But here's the problem. When you have a really high-powered lens, it is trying to catch light coming in at a very steep angle.
From the edges?
Yes. When that light travels from the glass slide up into the air, it bends. It refracts.
It bends outward.
Yes. It bends away from the lens. It effectively misses the bucket entirely.
Oh, wow. So the air is stealing your data.
The air is absolutely stealing your data. It limits the numerical aperture to a theoretical maximum of 1.0, but in real-world practice, you can rarely get it above 0.95.
So there is a hard ceiling on how much detail you can see if you are looking through air.
Exactly. This brings us to the limit of vision formula. The distance d equals 0.5 times lambda divided by NA.
So to make d the smallest visible thing smaller, you need NA to be bigger.
But the air locks you in at 0.95.
So how do we cheat? Because scientists clearly do see smaller things than that.
We cheat by simply removing the air.
Removing the air.
This is the aha moment for immersion oil.
The oil. Okay, I always saw scientists doing this in movies, putting a drop of goo on the slide and dunking the lens right into it.
Yes.
And I always just assumed it was some kind of lubrication, like oiling a squeaky hinge or something.
No, not at all. It is purely optical engineering. That oil is specially formulated to have a refractive index of about 1.515.
Which is?
Which is almost exactly the same refractive index as glass.
Oh. So you were tricking the light.
You are bridging the gap. Optically speaking, there is no boundary anymore.
The air is gone.
Right. The light travels from the rock, through the glass slide, through the oil, and up into the glass lens, as if it were all just one solid block of material.
It doesn't bend.
It doesn't bend. It doesn't refract away. It goes straight into the bucket.
That is brilliant. It is such a simple workaround for a physics problem.
It really is. It allows the numerical aperture to jump from that 0.95 limit all the way up to 1.4.
That is a massive jump.
It is a massive jump in resolution.
Yeah.
Suddenly, that blurry blob resolves into two distinct points. You can see the internal structure of the crystal, all because you replaced a millimeter of air with oil.
Now, while we were talking about extreme precision, I have to mention one specific detail from the Wraith text.
Oh, which one?
It made me laugh because of how oddly specific it was. The cover glass.
Ah, yes, the cover glass.
The little square of glass you glue on top of the rock. The source states very firmly that it must be 0.17 millimeters thick.
Yes.
Not 0.16, not 0.18. It has to be 0.17.
I know it sounds like we were being incredibly pedantic.
It does a little.
But you have to remember, we are dealing with high-end optics here. That cover glass isn't just a lid to keep dust off the sample.
It's not just a protector.
No, it is an active optical component of the microscope.
It is part of the lens system itself.
It is. The engineers who designed the objective lens calculated the path of the light based exactly on the refraction caused by 0.17 millimeters of glass.
So if you mess with that thickness...
If you use a cheap cover slip that happens to be 0.2 millimeters thick, you introduce something called spherical aberration.
Which means what, exactly?
It means the light rays coming from the center of the image and the light rays coming from the edge focus at slightly different spots.
The image gets soft.
It gets hazy. You can turn the focus knob all day long, but it will never, ever be truly crisp.
Just because the glass was a fraction of a millimeter too thick.
Precision matters. When you are working right at the limit of physics, you really have to follow the rules.
Okay, so we have our machine built, we have our oil applied, we have our exact 0.17 millimeter glass.
We are ready.
Now we need to turn on the light. But not just any light. We need polarized light. This is section 2 of our deep dive, and this is where we really leave the high school biology class entirely behind.
This is where things get petrographic.
Right. Now, the GeoGirl source and the Liber texts both use the same analogy for this, and I think it's great because it works so well. The picket fence.
It is a classic analogy because it helps you visualize something that is completely invisible.
So walk us through it.
First, we need to understand that light is a wave. Normal light, like from a light bulb or from the sun, it vibrates in all possible directions.
Up, down, left, right, diagonal.
It is chaos. It's a mess.
It is like a messy rope being shaken by a hyperactive kid in every direction.
Yes, exactly. Now imagine placing a picket fence with vertical slats right in front of that rope.
Okay.
If you shake the rope straight up and down, parallel to the slats, the wave goes right through. It slips between the pickets.
Makes sense.
But if you shake it side to side...
It smacks into the wood and stops.
Exactly. The fence filters the vibration. That is exactly what a polarizer does in our microscope.
So the microscope has a literal filter.
Yes, located below the stage, before the light even hits the rock sample.
Okay.
It usually acts like a horizontal fence.
Yeah.
It only lets the east-west vibrations through.
So now we have this very orderly east-west vibrating light hitting our rock. But there's a second fence involved, isn't there?
The analyzer.
The analyzer.
This is a second filter, and it is located above the rock, between the objective lens and your eye.
And here's the trick, right? The analyzer is oriented north-south.
It is perpendicular to the polarizer.
So if the first filter is an east-west fence, the second filter is a north-south fence.
Exactly right.
So let's do the thought experiment for the listener. I have no rock on the stage, just air.
Okay.
The light goes through the first fence. It is now vibrating east-west. It travels up to the second fence, which is north-south. What happens?
It gets blocked completely.
Boom, stopped.
The second fence stops whatever the first fence let through, because you have crossed the fences.
The result is total darkness.
Yes. If you look through a petrographic microscope with crossed polars and no sample on the stage, you just see black.
That is our blank canvas. Blackness.
Yes. And this is the most critical concept to grasp in all of optical mineralogy.
Why?
Because if you put a rock in there and suddenly you see light.
That means the rock did something to the light.
Exactly. The rock physically changed the vibration direction of the light so that it could sneak through that second fence.
It twisted the light.
It twisted it. And this brings us to the two main categories of minerals. The sources refer to them as isotropic and anisotropic.
Okay, let's break those down. What is isotropic?
Isotropic minerals are the polite ones. Think of materials like glass or minerals with a cubic crystal structure, like garnet or even diamond.
Polite meaning what?
Meaning their internal atomic structure is perfectly symmetrical in all directions.
So the atoms are spaced evenly, like a perfect grid.
Basically, yes. The electron clouds are completely uniform, so when light passes through them, it doesn't get twisted at all.
Well, it enters vibrating east-west, and it leaves vibrating east-west.
Exactly.
So if I take a diamond and put it under the microscope with the crossed polars...
It stays black.
Really?
Yes. The light gets blocked by the analyzer, just as if the diamond wasn't even there. Optically speaking, in this specific mode, the diamond is invisible.
That is wild. But most minerals aren't like that.
No, they are not. Most minerals, things like quartz, feldspar, mica, they are anisotropic.
Which means they are not symmetrical.
Right. Their crystal structure is squashed or stretched in certain directions.
Yeah.
The atoms are packed tighter one way than another.
So the lattice itself is directional.
Correct. So when that incoming east-west light hits this highly asymmetric lattice, the crystal essentially says, no, I don't like east-west.
And it forces a change.
It physically splits the light beam into two separate rays that vibrate in directions the crystal does like.
It splits and twists the light.
Ideally, yes. So by the time the light finally exits the top of the crystal, it is vibrating in a totally new direction. It now has a north-south component to it.
So when it hits the analyzer...
Some of it can finally pass right through that north-south fence.
And that is why, when we look through the scope, we see the crystal suddenly glowing against the black background.
Exactly. We have forced the rock to reveal its internal structure by twisting the light. We are quite literally seeing the interaction between the atomic lattice and the photon.
Okay, so we have our setup. Now let's talk about what we actually look for when we peer into the eyepiece.
The diagnostic techniques.
Right. The outline breaks this down into two distinct viewing modes. Plane-Polarized light, or PPL, and Cross-Polarized light, XPL.
Right. PPL is when we take the analyzer out of the light path completely.
So we were just looking with the single lower polarizer.
Yes, there is no black background here. The background is just bright white light.
This seems a bit more like normal viewing to me. What are we actually looking for in PPL? The first thing mentioned is relief.
Relief is a measure of how strongly a mineral grain stands out against its background medium.
Usually they are mounted in some kind of epoxy or oil. Right.
Exactly. Now, if the mineral has a refractive index that is very different from that surrounding oil, it looks very bold.
Bold how?
It has these thick, dark outlines. It looks like it has a rough surface, almost like 3D topography sticking up at you.
We call that high relief.
Right.
And if it has the exact same refractive index as the glue it's sitting in?
It practically disappears.
Yeah.
It looks flat, smooth, almost entirely invisible. That is low relief.
It's like the Invisible Man.
That is a perfect analogy. You can only see the Invisible Man because of the clothes he is wearing. If the clothes, the relief, match the background perfectly, he vanishes.
There's a really cool trick mentioned in the texts to measure this. It's called the Beck line.
Ah, the Beck line method. This is the very first magic trick you learn in geology school.
How does it work?
If you want to know if a mineral has a higher or lower refractive index than the oil sitting right next to it, you find the edge of the grain.
Okay, you center on the boundary?
Then, you slowly lower the stage. You intentionally defocus the microscope.
You make it blurry on purpose.
Just slightly. And as you do that, you will see a very bright line of light. A halo physically move.
It sweeps across the boundary.
Yes. And if the halo moves into the mineral grain, then the mineral has the higher refractive index.
Halo in high.
Halo in high. That is the mnemonic every geology student repeats in their sleep.
Why does the light do that? Why does it form a moving halo?
Because the mineral grain acts like a tiny primitive lens itself. If it has a higher index, it focuses the light inward as you change the distance. If it has a lower index, it diverges the light outward.
You are literally watching the light bend in real time.
You are.
The other big diagnostic feature in PPL is pleochroism, which sounds like a medical condition, honestly.
It does a bit.
But I gather it is about color.
It is the color-changing magic trick. We mentioned earlier that anisotropic minerals absorb light differently depending on the direction.
Right.
Well, some of them absorb specific colors differently depending on the direction.
Give me an example of that. What does it look like?
Bigotype mica is the classic example. It is a sheet silicate, like pages in a book.
Okay.
If the polarized light hits those sheets one way, the mineral absorbs almost everything and it looks dark brown.
Very dark.
But if you just rotate the stage 90 degrees so the light hits it differently, it suddenly lets the light through. It looks pale yellow or even clear.
So as I physically spin the stage under the lens, the rock is just blinking at me.
It is blinking at you. Brown, clear, brown, clear.
That is incredible.
And that is incredibly diagnostic. If you see a mineral doing that, you can instantly rule out 90% of the other possibilities. You say, okay, that is biotite or that is hornblende.
It is a dead giveaway.
It saves you hours of guessing.
Okay, now let's push the analyzer back in. We are engaging cross-polarized light, or XPL.
The background goes pitch black.
And the minerals suddenly light up. And this is where we see colors that just shouldn't be there.
The neon colors.
Right. Neon blues, bright magentas, yellows. But the sources are very emphatic about this point. These are not the actual colors of the mineral.
No, they are absolutely not pigments.
If I crunched that pink rock, the powder wouldn't be pink.
It would probably be white or gray. These colors are known as interference colors. They are pure artifacts of physics.
This is where the physics gets a little trippy for me. We need to talk about retardation.
Right.
And in physics, retardation implies a delay, right? A lag.
Correct. Retardation simply means one light wave is lagging behind another. Remember earlier I said the anisotropic crystal splits the light into two distinct rays.
Yes, the two rays vibrating in perpendicular directions.
Well, here's the kicker. Those two rays do not travel through the crystal at the same speed. You have a fast ray and a slow ray.
So it is essentially a race through the rock.
It is exactly a race. They start at the bottom of the crystal at the exact same time. But as they travel up through that dense crystal lattice, the slow ray gets dragged down by the electron clouds.
It faces more resistance.
Yes, so it falls behind. By the time they both exit the top of the crystal, the slow ray is a certain measurable distance behind the fast ray.
And that distance is the retardation.
Yes, represented by the Greek letter gamma.
But why does that lag create a color? Why magenta or blue?
Because of wave interference. When those two out-of-sync rays hit the final analyzer up top, they are forced to recombine.
But because one is lagging, they don't line up perfectly anymore.
Exactly. The peaks and valleys of the two waves are completely offset, and if lag distance is just right, the peak of one wave perfectly meets the valley of the other wave.
They cancel each other out.
That is destructive interference. They annihilate each other.
So certain colors just vanish from the white light?
Yes. For example, if the retardation distance is roughly 550 nanometers, you perfectly cancel out the green wavelengths.
Okay, so if you take full white light and you subtract green, what does your eye see?
What do you see?
Magenta, like a purple pink.
Exactly. So that bright neon pink you are seeing on the microscope is not a pink pigment. It is just white light minus green.
That is completely mind-bending.
The color is literally a speedometer reading. It tells you exactly how far behind the slow ray got during the race.
And that lag time depends on two factors, right? How slow the mineral inherently is.
Which is a fundamental property called Birefringence.
Right. And the second factor is how long the racetrack is.
The length of the racetrack is the physical thickness of the rock slice.
Which brings us to the formula. Retardation equals birefringence times thickness.
Gamma equals delta n times d. Yes.
And this connects perfectly back to why the thin section has to be so uniformly thin. The Wraith text was practically obsessive about the 30-micron standard thickness.
This is exactly why. If your rock slice is perfectly 30 microns thick, a mineral like quartz will look gray.
Gray, okay.
But if you cut it carelessly, and let's say it is 50 microns thick.
The racetrack is longer.
The racetrack is much longer. The slow ray falls even further behind, the retardation increases, and suddenly your quartz turns bright yellow.
And you look at it and misidentify the mineral entirely.
And then you map the geology wrong. Or worse, you tell an oil company to drill a dry well. Millions of dollars wasted.
All because the slice was 20 microns too thick.
The uniform thickness is what allows geologists all over the entire world to speak the exact same color language. Gray quartz in New York is gray quartz in Tokyo.
Now, I noticed in the Wraith text they mentioned a slight change in how we write down birefringence.
Yes, nomenclature shifts over time. Older texts often used a lowercase delta for birefringence.
But the newer standard...
The newer Wraith standard uses delta n. It is a small detail, but mathematically it is much cleaner.
Because it represents a difference.
Right. Birefringence is literally the difference between the high refractive index and the low refractive index of the crystal. So using a delta, which implies difference in math, makes logical sense.
Okay, there is one last visual phenomenon in XPL that we need to cover. Extinction.
Ah, extinction.
As you rotate the stage, this bright, glowing neon mineral suddenly goes completely dark.
4 times per full rotation, every 90 degrees.
Why does it do that? I thought we established that anisotropic minerals always twist the light.
They do twist the light, unless they are lined up perfectly with the filters. Remember, the filters are set strictly north-south and east-west. If the internal vibration directions of the crystal itself align perfectly north-south and east-west...
The light doesn't get split?
Correct. It passes straight through the east-west channel without being split, and then it hits the north-south analyzer and gets completely blocked.
So it momentarily acts like it's isotropic.
We call that moment extinction.
So as you spin it, it's just blinking on and off, light, black, light, black.
And the specific angle at which it goes black relative to the crystal's physical shape, that is another massive diagnostic fingerprint.
So you measure the angle.
You measure it. Is it parallel extinction? Is it inclined? Symmetrical? It helps you tell a feldspar from a pyroxene in seconds.
It really is detective work. You are literally measuring angles of darkness to figure out the name of the suspect.
It is geometry and physics applied directly for identification.
Okay, let's leave the high-tech microscope lab for a moment.
Let's get our hands dirty.
Because sometimes you do not have a $10,000 piece of German optical engineering handy in your backpack.
Usually you don't.
Sometimes you're out in the field and you just have a rock and a little plastic bottle of acid.
The field test. Low-tech, high-impact.
This is Section 5, the acid and fizz.
A geologist's best friend.
The source from Scribd was very practical about this.
Yeah.
It is basically using raw chemistry to spot carbonates.
Specifically, calcium carbonate, CaSO3. That is the mineral calcite, which is the main ingredient in limestone and marble.
And the weapon of choice here is hydrochloric acid.
Dilute HCl, usually just 5% to 10% concentration, or in a pinch, you can even use household vinegar.
Though the vinegar reaction will be much weaker.
And slower, yes.
So walk us through the actual reaction. You are holding a rock, you drop a bead of acid on it. What happens?
You are initiating a rapid chemical reaction. The hydrochloric acid reacts directly with the calcium carbonate.
It breaks the chemical bonds.
Right. And one of the main byproducts of breaking those bonds is carbon dioxide gas, CO2.
And gas takes up significantly more space than solid rock.
So it has to forcefully escape the liquid. It bubbles up. It effervesces.
It fizzes.
It fizzes vigorously. If you drop acid on a rock and it immediately foams up like an Alka-Seltzer tablet, you have calcite.
So it is almost 100% diagnostic.
It is very reliable. But there is a well-known catch.
The Dolomite problem.
Dolomite, the stubborn cousin.
What is Dolomite?
Dolomite is a mineral very, very similar to calcite, but it has magnesium integrated into its crystal lattice.
So it's calcium, magnesium, carbonate.
Exactly. And that magnesium-oxygen bond is physically stronger. It is much more stubborn.
So it resists the acid attack.
Yes. If you drop cold, dilute acid on a solid chunk of dolomite, it usually just sits there. You might see 1 or 2 tiny bubbles form over a few minutes if you use a hand lens, but mostly
nothing happens.
nothing happens.
So how do you tell the difference in the field? Because a rock that doesn't fizz might just be a regular piece of granite.
Right. You have to actively help the reaction along. We call the scratch test modification. You take a steel masonry nail or the blade of a pocket knife, and you scratch the surface of the mineral pretty hard to create a little pile of fine white powder.
You are drastically increasing the surface area.
Drastically. You are breaking down those strong surface bonds mechanically before the acid even touches them.
So you have a pile of dust, then what?
Now, you drop the acid directly onto the powder.
And if it fizzes then?
If the powder fizzes but the solid rock didn't, it is almost certainly dolomite.
And if the powder still doesn't fizz at all?
Then you can confidently say it is probably not a carbonate mineral at all. Move on to other tests. Maybe it's quartz or feldspar.
It is a very satisfying physical test. There is something wonderfully definitive about it. Fizz equals yes. No fizz equals no.
It is one of the few truly black and white tests in field geology. Well, fizz and no fizz.
And Lanny-wise, I mean, we are literally handling acid in the middle of nowhere.
Dilute HCl is relatively safe compared to the concentrated stuff you find in industrial labs, but it will definitely sting any cuts on your hands.
And your clothes.
It will absolutely eat holes in cotton clothes if you spill it. I have personally ruined many pairs of good field pans this way. You wash them, and suddenly they look like Swiss cheese.
Good to know. And obviously, as the outline joked, you do not taste the rocks.
No, even if they look like delicious rock candy.
Especially then.
Some beautiful minerals are arsenic or lead-based. Geology is a visual and chemical science, not a gustatory one. Do not lick the rocks.
Okay, fair warning. So, we have looked at the rock with light. We have attacked it with acid. We know exactly what it is.
We have identified the suspect.
Now comes the part that maybe doesn't get the glory of field discovery, but it is what makes the science actually possible over the long term. Cataloging.
The bureaucracy of science.
We are looking closely at DOI Museum Property Directive 20, and honestly, this sounded dry at first glance.
Most government directives do.
But as I read it, I realized something profound. We just spent an hour talking about destroying rocks, cutting them into slices, dissolving them with acid.
Yes. Science is often destructive.
If you don't preserve the data properly, that rock died for absolutely nothing.
That is exactly the point. A pile of rocks sitting on a shelf without labels is just gravel. It has zero scientific value.
That's just decor.
Right. If I hand you a stunning piece of granite, but I cannot tell you exactly where on Earth it came from, it tells us absolutely nothing about the Earth's history. It is just a very heavy paperweight.
The directive spends a lot of time talking about the scope of collection, this idea that museums shouldn't just be hoarders.
Right, because you cannot keep everything.
Yeah.
It's physically impossible. A museum needs a rational, defined plan.
Like, are we collecting this for research or for a public exhibition?
Exactly. If a random rock someone brings in doesn't fit the stated mission of the institution, you shouldn't just stash it in a drawer just in case.
That is how you get endless backlogs.
Backlogs, lost data, and wasted funding. It's about being highly intentional with what takes up space.
And the data fields themselves, the mandatory data section. It is not just writing rock, big on a tag.
Not quite. You need an accession number. That links the object to the legal transaction of how the museum actually acquired it, and you need a catalog number. That is the unique ID for that specific physical object. And most crucially, location data.
The outline made a joke about labels reading somewhere near the big tree.
You laugh, but historical collections are completely full of labels exactly like that, found near the old Smith farm. 1890.
Well, where was the Smith farm?
Exactly. It's a shopping mall now.
So the data is useless.
Modern science requires hard coordinates, latitude and longitude, UTM, township and range. We need to be able to go back to that exact spot on a map to verify the local geology.
There was a term in the directive that sounded very elite, very important. Type specimen.
Ah, the type specimen. That is the holy grail of any museum collection.
What does it mean?
In biology, or paleontology, or mineralogy, when a scientist discovers a brand new species or mineral, they have to designate one single physical object as the absolute definition of that name.
That is the holotype.
That is the holotype.
It is like the reference meter bar in Paris, the standard for all others.
Exactly. If anyone in the future ever argues about what a Tyrannosaurus rex actually looks like, or what a specific mineral is, they do not look at a textbook. They go straight back to the original type specimen.
Wow.
If you lose that specific object, you essentially lose the baseline definition of the species. So these are always classified under strict rules as controlled property, high security, high value.
I also found the distinction between lots and items to be really practical, because if you are an archaeologist and you find 1,000 tiny pottery shards in one hole, you do not have to sit there and write 1,000 separate catalog cards.
Thankfully, no. You can catalog them together as a single lot. One catalog number for the entire bag.
But if you have something like a pot and its matching lid,
Then they get the same core number but with suffixes,
yeah,
like 101A and 101B.
that keeps the physical relationship intact in the database.
It tells the future researcher, hey, these pieces belong together. Do not separate them.
And speaking of the database, the final piece is preserving the records themselves. The shift from old paper cards to the ICMS, the Interior Collection Management System,
We are constantly fighting a war against digital obsolescence.
because paper burns or rots.
But digital files can just as easily become totally unreadable. Have you tried to open a file from a 1990s floppy disk lately?
I do not even have a drive that could read one.
Exactly. The hardware disappears, the software updates, so the directive mandates strict offsite backups and constant digital migration.
You have to keep moving the data forward.
We have to actively migrate it to new formats so it doesn't get locked in the past. Science is essentially a multi-generational relay race.
We are saving this data for geologists who haven't even been born yet.
Exactly.
So let's bring it all back together now. We started this journey with a dusty gray rock from the driveway. We cut it open.
We put it under the Petrographic microscope. We use the lens formula to perfectly balancing those physical distances.
We used immersion oil to cheat the physics of air and boost our numerical aperture for high resolution.
We use polarized light to interrogate the atomic lattice. We watched for relief. We watched the Beck line move into the high-index mineral.
We watched for the blinking colors of Pleochroism as we spun the stage.
Then we crossed the polars. We watched the brilliant interference colors created by retardation, that lag of the slow ray.
We calculated the Birefringence. We recorded the extinction angles.
We even dropped some hydrochloric acid on it in the field to check for the fizz of calcite versus the stubbornness of dolomite.
And finally, we typed all of that heart-won data into a secure, migrating database so it never, ever gets lost.
It is a totally comprehensive toolkit for understanding the Earth.
So what does this all mean in the end? What is the real... So what here? Why go to all this immense trouble, the oil, the complex math, the acid, the bureaucracy, just for a sliver of rock?
Because a thin section is a frozen moment of deep time.
A frozen moment.
When I look at a rock under that petrographic microscope, I am not just seeing pretty neon colors. If I see a specific mineral that is deformed, physically twisted in the lattice, I am seeing the exact moment two continents collided and crushed this rock.
You are seeing the violence.
Yes. If I see a reaction rim where one mineral is slowly turning into another, I am seeing the magma cooling down millions or billions of years ago. I am reading the diary of the planet itself.
The colors are the code.
The colors are the code. And once you learn to read that code, you can look at that gray gravel on your path and realize that every single one of those stones has an epic saga locked inside it.
That is a genuinely beautiful thought. There was one last concept in the DOI text that I want to leave our listeners with today. The administrative definition of completeness.
Ah, yes. That's a profound one.
In the museum administration world, an object is defined as complete if it is whole. A perfect pot, a full skeleton.
Right.
It is labeled incomplete or just a fragment if it is broken. But in optical mineralogy...
In optical mineralogy, a fragment is everything. You do not need the whole mountain to understand the mountain. You do not even need the whole rock.
Just a slice.
A single microscopic grain of sand, sliced to precisely 30 microns, analyzed with polarized light, can tell you the exact temperature and pressure of the Earth's crust a billion years ago.
So a fragment can tell a perfectly complete story.
It absolutely can.
That is where we will leave it for today. Next time you see a boring rock, try to imagine the neon light show just waiting inside. Thanks for diving in with us.
Always a pleasure.